Hello, good morning, dear friends, dear students. In last video, we have seen the Boolean algebra part 1. Today we will continue the next part of this video, that is Boolean algebra part 2. I am here, Lalit Kumar P. Bhaiya, Associate Professor, Electronics and Telecommunication Engineering Department, Bharati College of Engineering and Technology, Durg. Let us go ahead for the Boolean algebra and corresponding solution of the digital equations, that is expressions, and minimizing the circuits. What we have seen in previous video, that we will review first and then we will go for the next part. This is the introduction about the Boolean. We have seen the operations and expressions for the Boolean, variables, complement, what are the variables, what are complements, what are literals, etc. We have seen this Boolean addition with the help of OR gate. We have seen Boolean multiplication with the help of AND gate. Laws and rules of the Boolean algebra. Three basic laws of the Boolean algebra we have seen: commutative laws, associative laws, and distributive laws. Commutative law is this: A plus B is equal to B plus A, that is A or B is equal to B or A. This we have seen. This is the commutative law of addition. Then commutative law of multiplication: A dot B is equal to B dot A. Then associative laws we have seen. Associative law for the addition: A plus in bracket B plus C is equal to in bracket A plus B plus C. This we have seen. Then associative law of multiplication we have seen: A into bracket BC is equal to in bracket AB and C. Distributive law, third law is distributive law, that is A into in bracket B plus C is equal to AB plus AC. That we have seen, and the circuit diagrams also seen. Then rules of this Boolean algebra, about 12 rules we have seen here. These rules, like A plus 0 is equal to A plus 1 is equal to 1, A dot 0 is 0, A dot 1 is equal to A plus A is equal to A plus A bar is equal to 1, A dot A is equal to A dot A bar is equal to 0, A double bar is equal to A plus AB is equal to A plus A bar B is equal to A plus B into A plus C is equal to A plus BC. That we have seen. And then we have also seen the De Morgan's theorem. The equivalency of NAND are negative OR gates and the equivalency of the NOR and negative AND gates. These two theorems we have seen. The complement of two or more ANDed variables is equivalent to the OR of the complements of the individual variables. That is, x dot y whole bar is equal to x bar plus y bar. And the second De Morgan's theorem is the complement of two or more OR variables is equivalent to the AND of the complements of the individual variables. That is, x plus y whole bar is equal to x bar dot y bar. These theorems we have seen. And the exercise on this De Morgan's theorem: apply the De Morgan's theorem on these particular equations that we have gone. Then Boolean analysis of logic circuits. Boolean algebra provides a concise way to express the operation of logic circuits formed by combination of logic gates, so that the output can be determined for various combination of the input values. Boolean expression for a logic circuit. To derive the Boolean expression for a given logic circuit, begin at the leftmost inputs and work forward the final output, that is from left to right, writing the expression for each gate. Here the one diagram is shown here, logical diagram. You can see two NAND gates are used and one OR gate is used here. The expression for the first AND gate is C into D. The expression for the OR gate is B plus CD. And the last one is A into bracket B plus CD is the final output of this logical circuit. So this type, then we have to apply the Boolean. Once the Boolean expression for a given logic, first of all, we have to construct the truth table for the logic circuit given. Once the Boolean expression for a given logic circuit has been determined, a truth table that shows the output for all possible values of the input variables can be developed. Let us take the previous circuit as the example. Here we have seen the output is A into bracket B plus CD. So let us take this example, A into B plus CD. So here 4 variables are there. Hence 2 to the power 4 is equal to 16. So 16 combinations of values are possible in this case. So evaluating the expression, to evaluate the expression A into bracket B plus CD, first find the values of the variables that makes the expression equal to 1. Expression equal to 1 using the rules of Boolean addition and multiplication. So we have to first make this expression equal to 1. How this can be done? We have to use the Boolean addition and multiplication. In this case, the expression equals 1 only if A is equal to 1 and B plus CD is equal to 1. Step by step you can see, if this A is equal to 1 and this bracket B plus CD is 1, then 1.1 will be equal to 1. Okay. Now, how this B plus CD becomes 1? Now determine the when B plus CD terms equals to 1, because we have considered here for this complete expression equal to 1, A and this bracket should be 1. But how this bracket, that is B plus CD equal to 1? Then the term B plus CD is equal to 1 if either B is equal to 1 or CD is equal to 1, or if both B and CD equals to 1, because this is ORing. Plus is there, B plus CD. So plus means ORing. So according to rule of the OR, any two things can be equal to 1 if both of them are equal to 1, or one of them are equal to 1. That is either B is equal to 1 or CD is equal to 1, or both B and CD equal to 1. So this B plus CD, that is 1 plus 0 is 1, B plus CD, that is 0 plus 1 is equal to 1, and B plus CD 1 plus 1 is equal to 1. Now the next one, how this CD becomes equal to 1? The term CD equal to 1 only if C is equal to 1 and D is equal to 1 as per the rule of AND gate, right? Then A into bracket B plus CD is equal to 1. When A is equal to 1 and B is equal to 1, regardless of the values of C and D, right? Then when A is equal to 1 and C is equal to 1 and D is equal to 1, regardless of the value of B, the expression A into B plus CD is equal to 0 for all other values combination of the variables. So this can be put on the truth table. You can prepare the truth table once you get this Boolean expression and their evaluation. So we have seen till now, for A into bracket B plus CD is equal to 1 is possible only when A is equal to 1 and B is equal to 1, regardless the value of C and D. CD may be 0. When A is equal to 1 and C is equal to 1 and D is equal to 1, regardless the value of B. B may be 0 or 1. Right? Then we can form, and this bracket A into B plus CD is equal to 0 becomes for all other combinations. So we can prepare this on the truth table, or we can have the truth table. Putting the results in the truth table format. You can see here A plus B plus CD is equal to 1, and I have already told you this. You can see this A plus B plus CD is equal to 1 becomes when A is 1, B is 1 regardless of C and D. And when A is 1, C is 1, D is 1 regardless of the value of B. So you can put this output 1. You can see A, B, C, D, and this is the output A plus B plus CD. So here you can put the output 1 on the, depending on this value, just we have seen A plus B plus CD is equal to 1. You can put here the values 1 as per these values. These are the possible combinations. 4 variables are there. Therefore, these are the 16 possible combinations, 0 to 15. Now, as per this, A is equal to 1, B is equal to 1, regardless value of CD. That means you require A is equal to 1, B is equal to 1. These are too important. So here you can say this is A is equal to 1, B is equal to 1. These are the values. So regardless of these values, this output will be equal to 1. So this is 1, 1, 1, 1, 1, 1, 1, 1. A is equal to 1, B is equal to 1. Regardless value of this one. So this is equal to 1. You can put here 1 at the last 4 values. Here 2, 3, 4. Last 3, 4 will be equal to 1. And then when A is equal to 1, C is equal to 1 and D is equal to 1. Regardless the value of B. So you don't bother about this one, and this 3 will be equal to 1. So this value you can see this is 1, this is 1, this is 1. This will be also equal to 1. Right? Regardless value of the B. Only this one combination is there. So last 5 will be equal to 1. You can see I have put here A, putting the results in the truth table A plus B plus C D. When A is equal to 1 and B is equal to regardless value of the C and D. I have already told you this one. And again you go for this regardless of the value of this CD, regardless value of this B. This is 1, this is 1 and this is 1. You can put here this one. So this is the combination of 1 and all other remaining will be equal to 0. So all other will be equal to 0. So in this way you can put the output 0 and 1 and complete the truth table. So this is the truth table for the given logic circuit, right? So you can go through this video and see this one. If you want to note down it, you can note down from this video, or if you require you can ask me, please, right? Then we have already seen this circuit. You can see this circuit. We have gone this circuit. Such type of, there may be a number of circuit, and this circuit will provide the Boolean expression, logical expression A into B plus CD, and we will go with the Boolean algebra. If applicable, we will use the De Morgan's theorem also. Similarly, number of circuits may be there, logical circuits, by which we can develop the different types of logical circuits and equations, and optimize the particular equations so that we can prepare the optimized circuits, right? For that we use the gates. Just we have seen AND gate and OR gate are used in the previous circuit. So we have already seen in the previous videos the logical gates which are used. So digital logic circuits are electronic circuits that are implementation of some Boolean functions, right? A circuit is built up of gates. Each gate implements some simple logic function. The term gates is named for Bill Gates in much the same way as the term gate is named for AEI Gore, the inventor of the internet, right? You can see here a gate where A and B are the inputs and output is a function of A and B as an input, right? Gates compute something. The output depends on the inputs. If the input changes, the output might change. If the input don't change, the output does not change. This is, we have already seen. This is called an OR gate, symbol of OR gate. A and B are the inputs. Then A plus B, that is A OR with B. This is called as ORing. In rough language, we can say plus. A plus means it is a digital plus, logical plus, right? OR, A ORing B. This is AND gate. This is called as multiplication, logical multiplication. And this is the symbol used for the logical multiplication. A and B are the inputs. This is A dot B. This is the multiplication. Or ANDing, A ANDing with B. This is NOT gate or inverter that we have also seen. A, here this arrow is shown and this is bubble is here. This will be A bar. If 1 is applied, you will get 1 bar is equal to 0. 0 is applied, then you will get 0 bar is equal to 1. This is inverter. That is called as a NOT gate, right? Then NAND or NOR gates. These are the universal gates because from this gate you can prepare any other remaining gates. This is the A and B are the input. This is the AND gate followed by this NOT. This is the NOT. Bubble is shown as a NOT gate. So A dot B is the output of the AND and the inverter shows the bar. So A dot B bar is the NAND gate. And similarly, this is R followed by the NOT. That is R, A plus B is the output of the R and followed by NOT is the bar. So A plus B bar. So this is the NOR gate, NAND gate and NOR gate, right? So NAND gate symbol and NOR gate symbol, you can do this one. Here, exclusive OR, we have also the another gate is called as the exclusive OR. Or simply it is written as a XOR in short form. Gate are shown here in below. This is the XOR gate. Distinctive shape. You can show symbol like this. This is R and this is like a cross of X. A and B is the input. X is the output. And this is the rectangular outline with the XOR gate. So there is no need of this rectangular outline. You can just know this symbol of the exclusive OR gate. Then what is the expression for the exclusive OR gate? That is also important. So here for an exclusive OR gate, output X is high when input A is low and input B is high, or when input A is high and input B is low, right? That means the if A and B are the input, then A into B bar plus B into A bar is the output of the XOR gate, right? So here you can see if both the inputs are low, output will be low. If both the inputs are high, output will be low. And if one of the input is high or low, output will be high. One of the input is high or low, output will be high. So you can prepare this truth table. If both the inputs are low, output will be low. And if both the inputs are high, output will be low. If one of the input is high, the output will be high. This is the truth table for the exclusive OR gate, right? And similarly, you can prepare the exclusive NOR gate just opposite of this one. This is XOR and followed by NOT gate. For an exclusive NOR gate, output X is low when input A is low and input B is high, or when A is high and B is low, X is high when A and B are both high or both low. So this is the X NOR gate, and this is the operation of the X NOR gate. When both the input is low, output is high. When both the input is high, output is high, right? And when one of the input is low or high, output will be low. These are the four possible combination, and this is the truth table. If A and B is 0, 0, then output is 1. If A and B is 1, 1, then output is 1. Otherwise, it is 0. Right? So, this is all about this gate and logical families along with this circuit diagram. So, dear friends, if you have any doubts on this Boolean algebra and De Morgan's theorem, which is a very important part of your syllabus, you can ask me your doubts at any time. You can ask any doubts on my phone also, and please prepare the notes on this particular things. I can provide you the PPT of this also if you require. Otherwise, you can go through the video on the YouTube channel of the Bharti group and share it, like it, and do the study properly. Okay. So thank you very much for your watching this video, and we will go for the next topic in the next video. Thanks a lot. Thank you very much.